Hey class, welcome back. This is the second, the second lecture. So lecture 2 for gas laws. So just want to make sure that, because I'm starting off with a blank page. So where we left off from the last lecture, we learned about two particular gas laws. First, we learned about Boyle's law, right, which states that pressure and volume are indirectly proportional to one another. So essentially, as pressure goes down, volume will go up if temperature and the number of gas moles stay the same. So the equation that we use for that is P1V1 equals P2V2. We also learned about Charles' law. And Charles' law states that volume is directly proportional to temperature if the pressure and the number of gas molecules stays constant. Okay, so these are the two gas laws that you've learned so far, and what I'm going to introduce to you now is the combined gas law. Okay, and the combined gas law is basically this guy right here and this guy right here combined. So as you can see, if we just want to combine the two, if we want to have, let's, for Boyle's law, P1 V1 equals P2 V2, and then if we want to combine that with Charles' law, right, V1 is already in the numerator, so it's just going to be P1 V1 over T1 equals P2 V2. Again, V2 is already in the numerator, so we can just put T2 in the denominator. So this is the two gas laws combined into the appropriately titled gas law. So what you'll notice too here is that we are always going to assume that number of gas moles are constant. Okay, so again, this is the combined gas law, and obviously this is the combined gas law encompasses both Charles and Boyle's law. The amount of gas just held constant, and just to let you know, temperature T1 and T2 are always in Kelvin. So an example, a sample of gas has an initial volume of 158 milliliters. So again, I think initial volume. So I'm thinking that's going to be, if it's initial volume, that's going to be my V1. So V1 equals 158 ml, and a pressure of 735 millimeter mercury. So that's going to be my P1. It's this guy right here, because it says an initial volume at a pressure of, so I'm assuming that's my P1. So that's 735 millimeter mercury, all right, and a temperature of 34 degrees Celsius. So that's my T1. So I'm always just going to take 273, right, because I always have to convert my temperature to Kelvin, and that's 34 degrees C. So that's going to give me 307 Kelvin. If the gas is compressed to a volume of 108 milliliters, so again, 108 milliliters is going to be my my V2. And heated to a temperature of 85 degrees, so that's my T2. So 273 plus 85, and we've got, it's going to equal 8, and then we have, right, yeah, 8, and then we have, so that's 358 Kelvin. Sorry. What is the final pressure in millimeters of mercury? Okay, so what is my P2? So we have all of our variables set up, and now all we have to do is rearrange and solve for P2. So the best way that you want to do that is, the easiest way, it's pretty simple. This one, you're just going to multiply both sides by the reciprocal of this, V2 over T2. So you're going to multiply both sides by T2 over V2 to cancel out V2 and T2. So if we do that, then our final equation is going to be T2, right, P1 V1 over V2 T1 equals P2, okay? So then all we have to do is, then now that we have our equation appropriately arranged, or so we're solving for the right value, all right, which is our final pressure. Then now all we have to do is plug in our numerical values. So I'm going to just do this right here. So I've got T2, T2, which is 270, yeah. Now that I have my calculator, I'm just double checking my math just to make sure. Yeah, 358. So I've got 358, oops, Kelvin multiplied by P1. And my P1 is 755 millimeter mercury. I can keep it at 755 millimeter mercury because my final pressure needs to be in millimeter mercury, so I'm good. And then V1 is 158 milliliters. And that's going to be over V2, and our V2 is 108. I like to keep things in parentheses just to keep it more visually straight. And then again we have our T1, which is 307, oops, Kelvin, okay? And before we plug this in our calculator, just want to make sure that our units cancel. And the relationships that we should see the same types of relationships in terms of proportional, not proportional, that kind of indirectly proportional kind of situation. So as pressure goes up, volume should go down, and as temperature goes up, volume should also go up. But what about, so we're looking again at pressure. So first of all, we want to make sure we're solving for pressure, so we want to make sure that all of our units cancel. So Kelvin cancels right here, milliliters cancel right here, and sure enough, our answer is left in millimeter mercury, which is what we want. And we're looking at the fact that, let's see here, our temperature started out at 307, okay, and it ended at 358, so it raised, right? But we don't have a direct relationship for temperature and pressure necessarily. We do know that if temperature goes up, pressure essentially should go up, because what are we doing? We're giving the gas molecules more energy, right? So if you give it more energy, and the collisions against the surface of the container or the sides of the container is going to increase, because the collisions are going to increase. But let's look at what's happening with volume. So our volume started off at 158 and it went down to 108. Okay, so the same kind of relationship here. Volume went down, so if our volume went down, our pressure should definitely increase. Okay, and that is also exemplified by the fact that, the fact that temperature goes up as well. Okay, so we're looking for an increase in volume. So we have 358 multiplied by 755 multiplied by 158, and all of that is over 108 multiplied by 307. And I have a pressure of 128, and it looks like we're working with 3 sig figs. So, well, here I'll show you what what my calculator gave me. 1,288.026, and again we're looking at 3 sig figs. So we got to stop here, which means that I have 1290, and that's millimeter mercury. Okay. So that's our final answer. So again, when we do these types of problems, it's the same type of process, right? You know, read the word problem, then I would assign the variables, then I would rearrange the equation to solve for the variable that we're trying to solve for. Okay, just like I did here. Then you want to plug in your numbers. You want to make sure that each type of unit is the same. So we have Kelvin and Kelvin, milliliter and milliliter, and that our answer is going to, and the way that I have this arranged, and the way that I have the units, that the answer is going to give us in millimeter mercury, which is what we want. But I also want you guys to think about what the answer should be, considering all the relationships that of gases, or conditions of gases, that we've learned. Okay. So here's this is from your book, okay, and again, 120, let's see, 125, did I do that wrong then? Let me make sure. It was 1.25, so that's the same. I have 129, so let me just make sure that I did this right. I will plug it in my calculator a little bit differently. What I'm going to do is I'm going to set up my equations slightly different. Oh, I see what I did wrong. This is my fault. I do this a lot. Sorry, guys. It's 7:35. So this 7:35, which this is now 7:35, and that'll give us a different answer. That'll probably give us the one. That's definitely why. 158. So sorry about this. Let me just double check. 07. Yeah. New answer. 1250 millimeter mercury. Okay? Sorry about that. All right, so this is from your book, right? And there's the final answer right there if you don't believe me. Okay, so that is the combined gas law. All right, what we'll do, we will go over more practice problems with the combined gas law, but during our actual Zoom meeting. But I'm going to go ahead and I'm going to move on, and I'm going to introduce basically, well, it's the second to last law. This is Avogadro's law, and it is relating volume and moles, all right? And so you can sit back and think of what is going to happen when the amount of gas changes, okay? So you can even think about it logically. I would sit back and say that if you increase the moles of gas, the volume, if you have a constant pressure and probably constant temperature, this is the situation, at a constant pressure and constant temperature, the gas, or the volume of a gas, is going to increase as we increase number of moles. Okay, so we have volume on that y-axis, number of moles on the x-axis, and you can see here as we increase our number of moles, volume is increased as well. And again, this is when temperature is constant and pressure is constant. So this is called Avogadro's law, obviously because we're dealing with moles, right? And just right off the bat, you can sit back and say, all right, well, probably what's going to happen is we're going to have some type of relationship where moles is going to be, one of the two is going to be an A. If either it's V1 over N1, equals V2 over N2, where N is our number of moles, all right? And V is volume. And here's the relationship right here. They're directly proportional. Again, this is called Avogadro's law. It came from Avogadro. And Avogadro's law assumes that obviously at constant temperature and pressure, that the volume of the gas is directly proportional to the number of moles. All right. So again, we have the number of moles in the numerator or denominator position, and we have the the volume in the numerator position. And then they have a picture of a kid blowing up a balloon to directly show you how volume increases as we increase the amount of gas. So when we exhale, right, into a balloon, we're putting more gas molecules in the balloon, and the volume of the balloon increases, all right? So that's how the balloon gets blown up. So here's a quick example. A 4.8 liter sample of helium gas contains 0.22 moles of helium. How many additional moles of helium gas should you add to the sample to obtain a volume of 6.4 liters? Assume, obviously, constant temperature and pressure. So what we're going to do is we're going to sit back and say that, all right, we know that we're using we'll go ahead and assign our units first. So we have a 4.8 liter sample of helium contains 0.22 moles of helium. So our V1 is going to be 4.8 liters. Our N1 is going to be 0.22 mole of helium. All right. Our N2, we don't know, but we do know our V2, which is 6.4 liters. So now what we're going to have to do is we're going to have to rearrange V1 over N1 equals V2 over N2 to solve for N2. So again, the first thing that I like to do is I like to multiply both sides by N2 to get N2 out of the denominator here. All right, so that gives us then, I'm just going to go ahead and erase, V2 equals V1 multiplied by N2 over N1. And then what I'm going to do is I'm going to then multiply both sides by this reciprocal. So I'm going to multiply both sides by N1 over V1. So that's going to cross cancel out this, right? And then we're going to have N1 over V1 right here equals N2. So I'm going to go ahead now and delete everything so you can see the final. So finally, N2 equals V2 over V2 multiplied by N1 over V1. So now what I'm going to do is I'm going to go ahead and plug in all of my variables. So I'm going to say N2 equals V2, which is 6.4 liters, multiplied by N1, which is 0.22 mole helium, over V1, which is 4.8 liters. Now again, make sure your units cancel. And before we finish this, we want to sit back and say really quickly, what do we think is going to happen? Okay, so again, the volume increased, right? The volume increased from 4.8 to 6.4 liters. So if the volume increases, then we should assume that the number of moles is going to increase as well. So I have 6.4 multiplied by 0.22, and that's going to be over 4.8. And sure enough, we end up getting a larger number out for moles, so 0.2933. And then again, we need 2 sig figs, so we're just going to go ahead and erase these two. And it's mole helium. And that is our final answer. All right. So again, same type of problem. Okay, Avogadro's law. What you need to remember is what this actually means. That is, volume goes up, number of moles should also go up. And so before you plug everything in, you want to make sure, first of all, that you arrange your equation appropriately to solve for the right variable. And then when you plug in your actual variables, your known variables, make sure your units cancel appropriately. And then before you plug it in your calculator, get a feel for what you think is going to happen with your knowledge of the law. Again, we know that this is Avogadro's law, has this type of relationship, so we should assume that number of moles will increase. And turns out number of moles do increase. So we did the problem correctly. Okay, so here is finally, sorry, I forgot to add this one part. Assume how many moles of gas should you add to the sample to obtain. So this is the number, this is our N final, right? So if N final is going to equal N initial, multiplied by X, okay? Or not added to X, sorry about that. So again, all I'm doing is I am finding out the number of moles that I need to add to get to my N final. My N final is 0.29. My N initial is 0.22. So X has to be 0.07 moles. So that technically is your final answer, okay? So obviously, again, make sure you read the problem correctly and completely before you start answering it. Rookie mistake. So here's our final answer right here. Okay, again, we'll do practice problems for Avogadro's law when we do our Zoom meeting. I'm trying to keep these lectures pretty short because they have been really long recently. So we'll do more practice problems again for Avogadro's law. But all right, so now what we're going to do is we're going to talk about this thing called the ideal gas law, which takes everything into account: pressure, volume, temperature, and number of moles. So essentially what the ideal gas law is, it's the combined gas law. Okay? The combined gas law with Avogadro's law thrown in. Okay? And this new variable called the proportionality constant, okay, which is R. All right, so let's take a look. So again, we have Boyle's law, right, which is volume is indirectly proportional to temperature. We have Charles' law, where volume and temperature are directly proportional. And then we have Avogadro's law, where volume and number of moles are directly proportional. So essentially, if we were to combine these, right, where we have volume on the left side of the equation and everything else on the right, the only thing that would be in the denominator would be pressure. So that's what we have here. All right. So basically what's going to happen now is there's this proportionality constant. Long story short, it's a gas constant to basically make sure that everything we can relate everything appropriately. All right, and we'll talk about it a little bit more in a second. So we plug this proportionality constant into it, then we can change this to an equal sign, and we have V equals RNT over P. But if we want to get P out of the denominator, over here, what we're going to have to do is we're going to have to multiply both sides by P. Right? This cancels. And then this will give us our final gas law of PV, right, equals nRT. Because we want to get, just to make it a cleaner thing, we want to get pressure out of the denominator. So the value of R is constant depending on the units that you're using. but it's called the ideal gas constant, and it's 0.0821 liters per ATM mole Kelvin. And it has to be all of these in order to cancel out, like it has to have all the units of volume, right, for liters, of pressure, which is ATM, mole for number of moles, and Kelvin for temperature, okay? So each of the quantities in the ideal gas law must be expressed in the units within R. Pressure must be expressed in atmospheres, volume must be expressed in liters, amount of gas must be expressed in moles, and temperature must be expressed in Kelvin, okay? Because this value for R has these units associated with them. Whenever you're using an equation or or you're solving a problem that requires PV equals nRT, all of your quantities must be in these units. There are other values of R with different units. Those have been experimentally determined. But in this class, for right now, we're going to worry about just using this one value of R. Okay? When you go into 200, you'll use different values of R. Different values for pressure will be maybe in millimeter mercury. Liters might be in a different unit. And essentially what will happen is R will then change. So this is the relation. You can kind of go over this and look through it yourself. We didn't talk about this law right here. All right, but that's okay. Essentially what we're looking at is we're looking at the fact that the take-home message for this chart is that PV equals nRT essentially keeps it encompasses all of the gas laws that we have already talked about. Okay, that's really the take-home message here. So R will always be given. It's not something that you have to memorize. It's always going to be given, so don't worry about it. But you'll use it so much, you'll probably just have it memorized anyway. So here's an example problem. So calculate the volume. So again, we're solving for volume, accompanied by a 0.845 mole of nitrogen gas. All right, so N equals 0.845 mole N2. So I don't know if you can hear that or not. Let me close my window. Hold on real quick. Sorry. Okay. So calculate the volume occupied by a 0.845 mole of nitrogen gas at a pressure of 1.37 atm and a temperature of 315 K. Okay, so this problem is super simple because here's the thing is, first of all, we don't have to change any one of these units. We don't have to convert them. They're all in the appropriate moles, right? Or units. They're all in the appropriate units, Kelvin, ATM, and moles, all right? And then the only thing that you have to memorize or remember is that we're always going to use R in this. So even though R isn't given, you're going to have to use R. So if you have a problem where you're given number of moles, pressure, and temperature, and you're not given a before and after, right? You need to think to yourself, oh, this is the ideal gas law, and you're going to have to incorporate R into the problem even though it's not explicitly given, all right? So again, just for good practice, I'll just put R equals 0.0821 liter ATM over mole. Okay, now what we're going to do is we're going to rearrange this guy to solve for V, and that all that we have to do in order to do that is just divide both sides by P to isolate V. So the final equation is going to be V equals nRT over P. Okay. Now what I'm going to do is I'm going to plug in my units. So V is equal to N, which is 0.845 mole N2. R is 0.0821 liter ATM mole Kelvin. T is 315 Kelvin, and that all of that's going to go over the pressure, which is 1.37 ATM. So here's the lovely thing about the gas constant. The gas constant, the proportionality constant, is there, right? Specifically also for being able to cancel out all of my units. So here I have mole N2, and you'll see it cancels out because mole is in the denominator of my gas constant. Same with Kelvin. Kelvin can cancel out because I have Kelvin in my denominator of my gas constant. ATM also cancels because I have it in the numerator of the gas constant. And that leaves the only thing left, which is liter, which is exactly what I want. I want my answer in liters. All right. So what we're going to do is we're just going to plug everything in. 0.845 multiplied by 0.0821 multiplied by 315 over 1.37. And that's going to give us a volume of, and I'll just write everything in my calculator from my, not every number, but I'll write a bunch, and then we'll round 95107. And again, that's in liters. And we are working with 3 sig figs here. So I have 1, 2, 3. So since I'm removing this 5, or dropping the 5, my 9 has to go up. So it's going to be 160 liters. So 16.0 liters is my final answer. Okay? So again, here's everything, 16.0 liters. Okay, so let's do another problem. Calculate the number of moles of gas in a basketball inflated to a total pressure of 24.2 psi with a volume of 3.2 liters and a temperature of 25 degrees Celsius. So calculate. So again, we're going to start isolating our variables. We're solving for N. All right. Pressure is 24.2. All right. So what you're going to have to do is you're going to have to convert PSI to ATM. All right. And what I'm going to do is, because I don't have that conversion memorized, I'm going to look at my table that I have at the beginning of this lecture. And if we have a PSI, okay, so 1 ATM is equal to 14.7 PSI. Okay, so 24.2 divided by 14.7, and that is going to give us, I'm going to squeeze this in here, 1.65. Okay, and again, because PSI canceled, right, and our answer's left in ATM. now we also have temperature that we have to deal with. So temperature is going to be equal, again, this was given in Celsius, so 273 plus 25 degrees C, and that's going to be 295 Kelvin, right? So, no, I'm sorry, 297, my bad. Yeah, 297 Kelvin. And then we have a volume of 3.2 liters right here. Okay, so that looks like that's everything. We can go ahead and, first, then we have to, well, I'll just make sure that we remember 0.0821 liter ATM over mole K for R. Now we need to rearrange everything and solve for N right here. So all we have to do is just divide both sides by RT. So N is going to equal PV over RT. So N equals, pressure is going to be 161.65 ATM. Volume is going to be 3.2 liters. R is going to equal 0.0821 liter ATM over mole K. And then we have temperature, which is 297 K. Okay, so then what we're going to do is we're going to go ahead and make sure all of our units cancel appropriately. Again, we want our answer in moles, so ATM is going to cancel because ATM is in the numerator of our R value, which is in the denominator. Okay, then liters are going to cancel for the same reason that ATM canceled, and then Kelvin cancels right here, so our answer is left in mole, which is what we want. Now you might sit back and say, well, wait a second, mole's in the denominator. Well, it's in the denominator of a denominator, so essentially it's going to be in the numerator of the answer. Okay, so we have 165 multiplied by 3.2, and that's over 0.0821 multiplied by 297. And that's going to give us, 0.2165. I'm just writing a bunch of numbers right now. And we're looking at 3 sig figs, so that's right here. So that's going to round to 0.21. Get rid of that. 217, and that's going to be mole gas. So 0.217 mole gas. Okay. So again, that should make intuitive sense to you guys too, because it's not necessarily, well, it doesn't necessarily make intuitive sense because we didn't have a before and after, but so I'm just going to move forward. All right, so here's the other thing. One more example, or one more type of ideal gas equation or calculation. We can, from the ideal gas law, we can calculate the molar mass of a gas, okay? So if you use that calculation in terms, if you use the ideal gas law in combination with a mass measurement, you can easily calculate the molar mass, right? So if you solve for N originally, right? Remember, molar mass is grams per mole, okay? So if you solve for N, and then you put N in the denominator, right? And then you have a certain given amount of mass, and then you put mass in the numerator, you can solve for the molar mass of the gas, okay? So again, obviously we're going to be rearranging this equation to solve for n, and just like we had up there, the previous example, we had n equals PV over RT, okay? And then what I'm going to do is I'm just going to go ahead and start assigning my variables. So a sample of gas has a mass of 0.136 grams. Its volume, right, is 0.112 liters. Its temperature is 298 Kelvin. So this is a pretty simple example too, because we don't have to do any unit conversions. And pressure equals 1.06 atm. And this is an ideal gas constant, or ideal gas law problem, so 0.0821 liters atm mole Kelvin, okay? And then what I'm going to do is I'm going to just plug everything in. So I have N equals P, which is 1.06 atm, V, which is 0.112 liters, R is 0.0821 liter atm mole Kelvin, and then multiply by temperature, which is 298 K. All right. Then we're going to do and make sure all of our units cancel right. So atm cancels, liters cancel, Kelvin cancels. Our answer is left in mole, which is what we want. And I'm going to plug this in my, calculator. Again, and we end up having 1.06 multiplied by 0.112 over 0.0821 multiplied by 298. And that's going to give me an N value of 0.0048524. And long story short, because we're working essentially with 3 sig figs across, we're stopping here, so I can just go ahead and erase that, right? And that's going to be in mole. Now, we can find what the molar mass is of this guy, right? By taking the grams, the mass in grams, which is 0.136 grams, and we'll put that over the answer that we arrived at for N, which is 0.00485 mole. And we have 0.136 divided by 0.00485 mole, and that's going to give us 28.04 grams per mole, right? No units canceled here, so we're bringing grams per mole over. So what is this? What is 28.04 grams per mole? So if you look at your periodic table, all right, so this could be a diatomic gas, or this could be a noble gas, right? And let me just, there we go. Oh, of course, the one periodic table that I bring up doesn't give me my molar masses, so hold on just a second. Right here. So we're looking at 28.04. So we can either, if it's 28.04, roughly, right, we can either sit back and say, is it one of the noble gases? And I don't see anything that's 28.04. So it must be some kind of diatomic. So if it's a diatomic, right, we need to take 28.04 and divide it by 2, and that's 14.02, and that's very close to nitrogen. So it's probably, the identity of this gas is probably N2. So, I'm sorry. And this makes a lot more sense too. I didn't round my significant figures just yet. So this final answer right here, this is 3 sig figs and this is 3 sig figs. So we're going to have to just drop that. So it's 28.0. Okay. Again, there is no noble gas that's 28.0. But if we take 28.0 and we divide it by 2, we'll get 14, which is the molar mass of nitrogen. So this gas is going to be diatomic nitrogen. Okay? So we talked about how we're using the ideal gas constant, right? And the ideal gas constant comes from all the gas laws, which comes from the molecular theory of gases. And remember I said at the very beginning of this lecture that we're going to focus on when that theory actually works and not really focus on the theory when it doesn't work. And so I just want to go ahead and say that when we talk about gases behaving ideally, that's when the theory works. When the theory doesn't work is when we recognize that gases are not always ideal. Okay, so what does that mean? An ideal gas law only works for gases that behave ideally, which means that two things. One, the particle size is small and the distance between the particles is large. All right, so the distance between the particles is large. And B, the particles do not interact with each other. Okay, so these two things are saying the same thing essentially, right? The particle size is small and the distance between the particles is large. So if the particle size is small and the distance between them is large, the likelihood that they are going to interact is going to be extraordinarily low. Extraordinarily low. And the other part is particles do not interact with each other at all. Okay, so basically these two things are saying the same thing. Ideal gases behave ideally when we can assume that the gas particles don't interact, okay? That they don't interact at all. But sometimes they do interact, okay? Sometimes they do interact. Under conditions of high pressure and low temperature, the interactions between gas particles become significant, right? This is where that intermolecular forces, intermolecular interactions come in. If we take a gas and condense it, right? High pressure, forcing the gas molecules closer together. Forcing them to go closer together. And then we have a low temperature, right? So high pressure and low temperature. So what's happening is when you decrease the temperature, you're slowing down the gas particles. So not only are they closer together, now they're slower. And now that they're slower, they can actually interact with each other in a substantial way. All right? So if we compress the gas to make them closer together, and if we cool down the gas to make them move slowly so that they do interact with each other, we have to then take into account intermolecular interactions into our equations. Ideal gases, the gases that we've dealt with throughout this entire chapter, we've assumed that the gases don't interact with each other. We've assumed that because we're assuming that particle size is small, right? And interactions between the particles are insignificant. So if we assume that the gas particles in general don't interact with each other, we don't have to take these intermolecular forces into account when we're calculating certain conditions, when we're predicting the behavior of gases under certain conditions. So this is a situation, low temperature and high pressure, when the ideal gas laws break down. And that's because we have to take into account these intermolecular interactions. And when we take these intermolecular interactions into account, then temperature might not always increase with increasing pressure, and volume might not decrease when we increase pressure, and all that stuff. It's not so cut and dry. All right. So this is, and that's all we're going to really talk about, right, with this situation. That's all we're going to sit back and say with the ideal gases not behaving ideally. So when they do behave ideally, that's under situations of high temperature, where the gas molecules are moving fast and they can just zoom past each other, right? And low pressure, where there's lots of space in between them. All right. Non-ideal gas conditions is when we take high pressure, we condense the gas molecules, we force them to interact with, or we force them to be in a smaller space, essentially. And low temperature, we slow down the gas molecules and essentially force them to interact. So again, all you need to know is what are the conditions when we have ideal gases versus the conditions when we have non-ideal gases. Ideal gases, we get that from high temperature and pressure, and non-ideal gases, we get that from low temperature and high pressure. So now we're going to move